Red-black trees are a type of self-balancing binary search tree designed to maintain efficiency in operations by keeping the tree balanced. Each node in a red-black tree is assigned one of two colors, red or black, which helps enforce specific properties that ensure the height of the tree remains logarithmic with respect to the number of nodes. This balance guarantees operations like search, insert, and delete can all be performed in O log n time, even in the worst-case scenario. Without such balance, binary search trees may degrade to linear performance, where the time complexity becomes O(n). The importance of red-black trees lies in their widespread applications in computer science. These trees are foundational in implementing balanced data structures such as maps and sets in programming libraries. They are also used in database indexing, maintaining routing tables in networks, and even in the design of compilers. Throughout this lecture, we will examine the key properties of red-black trees, their structural characteristics, and the operations that enable their balance, such as rotations, insertion, and deletion. The efficiency of red-black trees is ensured by 5 key properties. First, every node in the tree is either red or black, a foundational rule for enforcing balance. Second, the root node is always black, which provides stability and consistency in the tree structure. Third, every leaf node, represented by nil, is black, simplifying algorithms and edge cases during operations. The fourth property states that no red node can have a red child, preventing consecutive red nodes and ensuring even distribution of black nodes. Finally, the fifth property requires that all simple paths from a node to its descendant leaves contain the same number of black nodes. This uniformity limits the height disparity between different paths, ensuring that the tree remains balanced. These properties collectively define the red-black tree and ensure it operates efficiently. A red-black tree is composed of 3 main elements: internal nodes, leaf nodes, and the root node. Internal nodes are the primary components of the tree and contain key values, as well as color attributes of either red or black. These nodes form the core structure where most operations, such as search or insertion, occur. Leaf nodes, often called nil nodes or sentinel nodes, are placeholders that represent the endpoints of the tree. These nodes are always black and serve to simplify the implementation of algorithms, such as during insertion or deletion. At the top of the tree is the root node, which is always black, as required by the second property of red-black trees. This structure ensures the tree remains balanced, allowing for logarithmic time complexity in basic operations. The concept of black height is fundamental to red-black trees. The black height of a node is defined as the number of black nodes along any simple path from that node to a leaf, not including the node itself. This measurement is consistent for all paths from a given node to its leaves due to the fifth property of red-black trees. For example, the black height of the root determines the overall balance of the tree. A tree with n nodes has a minimum black height of log base 2 of n plus 1 and a maximum height of 2 times log base 2 of n plus 1. These constraints ensure that the tree remains balanced, providing the logarithmic efficiency required for operations like search, insertion, and deletion. The height of a red-black tree is bounded by its black height. In the worst-case scenario, the height of a red-black tree is no more than twice the logarithm of the number of nodes plus 1. For example, a tree with n nodes will have a maximum height of 2 times log base 2 of n plus 1. This property ensures that no path in the tree becomes disproportionately long, maintaining balance and efficiency. This approximately balanced structure is critical for the performance of red-black trees. By keeping the height logarithmic, these trees provide consistent and predictable performance for operations, regardless of the size of the dataset. This makes red-black trees a popular choice for implementing dynamic sets and other data-intensive applications. Rotations are a key operation in maintaining the balance of a red-black tree. There are 2 types of rotations: left rotation and right rotation. A left rotation adjusts the structure of a tree by moving a node and its child counterclockwise. Specifically, the right child of a node becomes its parent, and the node itself becomes the left child of its original right child. Subtrees that are affected by this rotation are rearranged to preserve the binary search tree property. Right rotation is the inverse operation, moving a node and its child clockwise. Here, the left child of a node becomes its parent, and the node itself becomes the right child of its original left child. Both operations ensure that the tree remains balanced by redistributing nodes. Importantly, rotations are local operations that involve only a constant number of pointer changes, making them efficient with O of 1 time complexity. Rotations are essential for restoring red-black properties after insertions and deletions. Insertion in a red-black tree involves three main steps. First, the node is inserted as an irregular binary search tree. This means finding the appropriate location for the new node by comparing its key to the existing nodes in the tree. Second, the new node is initially colored red. Coloring it red ensures that no black height violations occur during insertion, as adding a black node could disrupt the balance. The third step is fixing any violations of the red-black properties that may arise. This step involves recoloring nodes and performing rotations as needed. The goal is to restore the properties, such as ensuring that no red node has a red child and that the black height remains consistent across all paths. The procedure RB insert fix-up handles these adjustments, ensuring the tree remains balanced and efficient for subsequent operations. When inserting a node, three main cases may arise that require fixing the red-black properties. In the first case, the parent and uncle of the new node are both red. In this scenario, the parent and uncle are recolored to black, and the grandparent is recolored to red. This recoloring resolves the immediate violation, but it may propagate the problem upward, requiring further adjustments. In the second case, the uncle is black, and the new node is a right child. Here, a left rotation is performed on the parent, converting the scenario into the third case. In the third case, the uncle is black, and the new node is a left child. The parent and grandparent are recolored, and a right rotation is performed on the grandparent. These cases collectively ensure that the tree remains balanced and all red-black properties are restored after insertion. Deletion in a red-black tree involves removing a node and restoring balance to the tree. First, the node to be deleted is removed as an irregular binary search tree. If the node has two children, its successor is identified to replace it. This successor is chosen to maintain the binary search tree property. After removing or replacing the node, the tree may violate the red-black properties. Fixing these violations involves recoloring and performing rotations, much like in the insertion process. The procedure RB delete fix-up handles these adjustments, ensuring that properties such as uniform black height and the absence of consecutive red nodes are preserved. Deletion is a more complex operation than insertion but is crucial for maintaining the efficiency of the tree. The RB delete fix-up process involves four main cases to restore the red-black properties after deletion. In the first case, the sibling of the doubly black node is red. Here, the sibling is recolored to black, and a left rotation is performed on the parent. This converts the scenario into one of the other cases. In the second case, the sibling and both of its children are black. The sibling is recolored to red, and the extra black is moved up the tree, requiring further adjustments. In the third case, the sibling is black, its left child is red, and its right child is black. A right rotation is performed on the sibling, converting it to the fourth case. Finally, in the fourth case, the sibling is black, and its right child is red. A left rotation and recoloring remove the extra black, restoring the tree's balance. These cases ensure that the tree remains a valid red-black tree after deletion. The time complexity of basic operations in a red-black tree is O of log n. For insertion, the process involves finding the appropriate position for the new node, which takes O of log n due to the logarithmic height of the tree. After the node is placed, the fix-up process, involving a constant number of rotations and recolorings, ensures the tree remains balanced without increasing the overall complexity. Similarly, deletion has a time complexity of O of log n. This includes locating the node to be deleted, which takes logarithmic time, and performing the necessary adjustments to maintain the red-black properties. Searching for a node, like insertion and deletion, also depends on the tree's height and thus takes O of log n. The balanced nature of red-black trees guarantees this logarithmic time complexity, making them highly efficient for managing dynamic datasets. Red-black trees offer several advantages that make them an ideal choice for various applications. First, they are self-balancing, which means the tree automatically maintains its balance through rotations and recolorings during insertion and deletion. This balance ensures that operations like search, insert, and delete always execute efficiently, even in the worst-case scenario. Another key advantage is their guaranteed performance. The O of log n time complexity for basic operations makes red-black trees highly predictable and reliable. Additionally, they are memory efficient, requiring only one extra bit per node to store the color. Their versatility is another strength, as they are suitable for a wide range of applications, including symbol tables, priority queues, and CPU scheduling. These advantages highlight the practical and theoretical significance of red-black trees in computer science. Red-black trees are widely used in various fields due to their efficiency and reliability. In databases, they are often used to implement balanced indexes, ensuring fast lookups and updates even as the dataset grows. Their self-balancing nature makes them ideal for maintaining consistent performance in dynamic environments. In operating systems, red-black trees are applied in process scheduling and memory management. Networking also benefits from red-black trees, where they are used to implement routing tables for efficient data transfer. In compilers, they are used in symbol tables to quickly retrieve variable or function definitions. These applications demonstrate the versatility and importance of red-black trees in optimizing complex systems across domains. When compared to other data structures, red-black trees provide a unique balance between performance and complexity. AVL trees, for example, also maintain balance and offer O of log n time complexity for insert, delete, and search operations. However, AVL trees require more rotations during insertion and deletion, making red-black trees faster in practice for scenarios involving frequent updates. In contrast, binary search trees have a worst-case time complexity of O of n when the tree becomes unbalanced. Red-black trees solve this issue by maintaining balance, ensuring consistent performance. Hash tables, while offering O of 1 average case time complexity, lack the order and flexibility of red-black trees. This makes red-black trees a preferred choice for applications requiring sorted data or range queries, such as in databases or networking. In conclusion, red-black trees are a powerful and efficient data structure that combines theoretical elegance with practical utility. Their self-balancing nature ensures that operations like search, insert, and delete always execute in O of log n time, regardless of the dataset size. This predictability makes them an excellent choice for implementing dynamic data structures. Moreover, their versatility enables their application in diverse domains, from databases and operating systems to networking and compilers. Understanding red-black trees not only deepens one's knowledge of balanced search trees but also provides a solid foundation for tackling real-world problems in computing. Their balance, efficiency, and broad applicability make red-black trees an indispensable tool in computer science.